So I'm going to discuss the phenomenological aspects of the model that Carlo has just presented. But I wanted to start with a picture from the original paper by Stephen Hawking, because Paul Davies reminded me that the title of the paper was... is it? Okay. Yeah, so the title of the paper was Black Hole Explosion, and with a question mark. And what I'm going to present now is black hole explosions, but in a new fashion. So let's wait for the slides. Yeah, very good. So I'm talking about quantum black hole phenomenology, and as you can see in the picture, there is a primordial landscape, because I'm going to focus on primordial black holes, and of course you see a big explosion that is maybe harming the poor dinosaur there. So let's start. Okay, so you have heard about this model, but let me rephrase it in one slide. So we start from the usual picture of in the Penrose diagram, in which you can see a singularity and a horizon, and of course there is some Hawking evaporation there. And the idea is that instead of a singularity, we replace the singularity with a quantum region. And so it's important to note that instead of an horizon, we have a trapping surface there. And then we wanted to take some approximations. In particular, we wanted to neglect the dissipative effects of the Hawking radiation. So of course, the Hawking radiation is there, but you can consider it as a secondary process with respect to the main quantum process, the bouncing one. If I remove the dissipation, then the process I have is a fully time invariant. The process I have is completely invariant under time reversal. So this means that I can take the time reverse process of a black hole, of the contraction of a collapse, that is a white hole, and I can glue it there in the future of the black hole. So I don't have just a trapping surface here, I have also an anti-trapping surface. So this is a surface from which everything has to go in, and this is a trapping surface, anti-trapping surface, that means that everything has to go out from there. And finally, in the simplified model that you have seen, following the lesson by Ajcek and Kiefer, the metric that has been written so far is a metric for a collapsing null shell. So of course, we needed to generalize this metric to a more complicated one, but for the moment, I already provide, for the first time, a full metric that describes this tunneling process. So maybe I can add here something that the idea is that, so you can see it as a tunneling, or another way that we have to see it is the fact that inside this quantum region, gravity becomes repulsive. So there is an effective force. You can write down effective equations, in fact, in which you have this repulsive force that appears in the quantum regime. And this is something that is well studied in loop quantum gravity, but seems to be a universal class, something universal to different approaches to quantum gravity. For instance, we see it also in asymptotic safety. So in my opinion, a good theory, whatever you like one approach or the other, you should ask to your theory of quantum gravity to account for this repulsive force in the deep quantum regime. And this is the way in which singularities, cosmological black hole singularities are solved. Okay, so the main feature, I think, of this model is this huge time dilatation. The fact that for an observer sitting at the center of at the center of the collapsing shells, the proper time of the process is just a few milliseconds, while seen from outside, it could be billion years. So this explains why, despite the fact that this model predicts that black holes will explode, of course we still see black holes there in the sky. It's just that they are like stars, exploding stars in very slow motion. Okay, so let me go back. I wanted to say something more here. So the most important, all the dynamics of the model is determined just by one parameter, that is the mass of the collapsing shell. Once you know the mass, you know everything about the model. But there is something missing, that is the relation between the mass and the lifetime of this dying black hole. And this is the crucial relation that we are trying to understand better right now. But because, so this means that once you have the lifetime of the black hole, you can derive its original mass, and basically you can say everything about the phenomenological properties you expect. So this lifetime should be computed in a full quantum theory. It can be used, it can be computed in loop quantum gravity. Maybe it can be computed also using semi-classical techniques. But in the meanwhile, we can in every case constrain the minimal and the maximal lifetime of these objects using some heuristic arguments. And the first heuristic arguments come from the notorious fireworks argument. That is the fact that our basic assumptions about physics, like unitarity, the equivalence principles, and so on, they cannot hold together once we go beyond a black hole that has lost more than half of its mass. So this means that, so this is a paradox. And we quantum gravitists, we used to think that quantum gravity should enter into the game before we find a paradox. So it means that something should happen before we reach the page time. So still the page time is of the order of m cube. So m cube is the lifetime that we used to have if the process was dominated by Hawkian evaporation. In this case, well, the maximal time is just half of this m cube, so still on the order of m cube. We have another argument to say what should be the minimal amount of time that this process should take, because as Carlo was explaining before, in order for this quantum process to happen, we need quantum effects to leak out of the horizon. So the lifetime should be long enough for this to happen. And this means that, Carlo has explained this very well, the fact that what is relevant is not just, what is relevant in order to enter in the quantum regime is not just the curvature, but the product of the curvature with time. And this means that it's enough for the lifetime to be of the order of m squared. So between m cube and m squared, there is a huge difference. And what we have done, what I will show you is a study for everything that can happen between these two values. So we have analyzed the phenomenology associated with all the possible explosion associated with the lifetime between m squared and m cubed. Yeah, okay. So as I said, the most important relation that we have to consider is this one, the relation between the mass and the time. And in particular, I can put the time, the lifetime, equal to the Hubble time, the age of basically the age of the universe, and so I can find back what would be the mass associated with black holes that are exploding now. So black holes whose explosion we can actually detect now. And there is a relation, of course, between, this is just the usual Schwarzschild radius that tells, once I have the mass, I know how big is the corresponding object. And so our idea was that the signal would be dominated by a wavelength that corresponds exactly to the size of the object that is exploding. So this radius here gives me the wavelength, the lambda, that I predict from the model. I call this a low energy channel for the model because there is also another possibility, namely that the total signal could have another component that comes directly from the particles, the photons actually, that created the black hole. So because of the fact that the process is very fast, so in the proper time of the particle falling in, the process takes a few milliseconds. So the idea is that those particles will come out with basically the same energy, the same temperature as they had when they followed in. So this means that if we are considering primordial black holes, those formed in the early universe, so the energy corresponding to this signal is in the TIV, so that is the energy corresponding to the temperature in the very early universe when those primordial black holes formed. Actually, this is very interesting because if this is true, this opens a new window to explore the early universe now. So you can, if the model was more reliable and more defined than what it is, this could provide us a way to make measures about what was the temperature of the universe at the time when primordial black holes formed. Okay, so there are a few characteristics that I want to highlight about the signal. Of course, the idea is that everything disappears after the burst. You don't have any further remnants, or you don't have an object there that can still emit something. So if you look for a repetition of the burst, or if you look for other emission, you will see nothing. And sorry, well, sure. The point is that I'm taking the point of view of somebody doing astrophysics. You want to distinguish this object from other objects. So, of course, if you see the same signal being repeated, this is not the kind of object I'm describing. Actually, there is a possibility that you have a repetition because there could be some lensing, but this is another story. This is also a possibility. This is also a possibility, yeah. I will discuss this later. It will enter in the discussion. So Okay, this is the main framework, and I wanted to put some numbers there because, yeah, okay, those are the numbers. So as Carlo was saying, the favorite model is the one in which the lifetime is m squared. So the corresponding primordial black hole for this lifetime is a black hole of 10 to the 23 kilograms. That is basically the mass of Venus. So it's the mass of a small planet. And this means in particular that, so if you believe that is the right value, you cannot observe burst corresponding to, so there should be no primordial black holes around that have mass smaller than this, because they have already exploded. So the fact that with the Kepler mission you don't see any primordial black holes smaller than this is compatible with this model. Of course, they have already exploded. Okay, so this is a mass that is not too small, not too big. It stays between the range of the standard range of primordial black holes, and its energy corresponds to this. So if everything would explode, all these mass would explode. It corresponds to this flux of big flux of energy. So now the question is, have we already seen something like this in the sky? Have the astronomers already detected something like this? Well, let me discuss the possibility of detection. And this is a recent work that is in collaboration with Barrault, Bollier, and Weimar. Weimar is a student here in Stockholm. So what we have done in this work was to consider, to study how far can we see the explosion. What is the maximum distance at which we would be able to see the explosion? So in this graph, so those graphs are one for the low energy channel and the other one for the high energy channel. This is the one related to the size of the black hole, and this is the one related to the temperature of the particles. So let me start from the one on your on the left. And what you can see here is this is the distance, and this is the lifetime. Well, this is the mass of the black hole that is parameterized with respect to the different lifetime. So here on the left you have black holes with the short lifetime, namely with the lifetime of m squared, and on this side you have a black hole with lifetime m cube. So what happens is that if the lifetime is m squared, sorry, basically we have access to all possible explosion in the whole universe, because you see the maximal distance is above the Hubble radius. So we have virtually access of all the explosion in the universe. Maybe you can notice some threshold in this graph. This is given by the fact that, so this corresponds to the optical band in which we have larger telescopes, so the detectability grows because of this. And this is a threshold that is due to the fact that this energy, we are beyond the QCD confinement, so there is the production of new particles, and in particular, we have the production because of the decay of the decay of pions, and this rises the photon productions in the process. So our best the possibility we hope for is actually this one, in which the detectability, the one in which the lifetime is very short and the detectability is very high. What about the high energy channel? So you see here, in most of the cases, the maximal distance is below the galactic scale. So this means that in order to observe the high energy component of the signal, we should have an explosion inside our galaxy, but of course this is less likely. So even if we would be in the favorite case in which the lifetime is very small, still in order to observe this component, we should be lucky to have an event happening very close to us. So the ideal situation is the one in which you see only one of the component, whether one or the other, depending whether the explosion is happening close to us or far from us. Yeah, so this is the most interesting part of what I am presenting here, because of course, how can we distinguish this, the signal associated with our model with respect to all the other astrophysical signals? Well, we have a smoking gun. And this smoking gun is provided by the relation between the wavelength observed and the redshift. So the more the explosion happens far from us, the farther is the explosion, the smaller should be the black hole, because the black hole should have had the time to explode, and then the signal should have had the time to travel to us. So this means if the black hole was smaller, the wavelength should be shorter for the signal associated with the low energy channel. So there is a shorter wavelength coming from this object, but at the same time, this wavelength is redshifted. And so the resulting observed wavelength is the one written there. And it's a very characteristic, it gives a very characteristic curve that is very flat. And this means that if one day we would have a statistics of those signals, we may hope to fit this curve. Okay. Well, actually, this is not. So this this was a smoking gun associated basically with the low energy channel. We have also a smoking gun for the high energy channel, that is the following one. So we have studied the integrated emission. So this means that we have considered the number of photons measured for a given energy in a given lapse of time for a given surface of our detectors. And so we have the integrated emission gives a characteristic shape of that is a distorted black body. Not just a black body, but a distorted one. And such a distortion is not, so it's characteristic of these objects. It's not, it doesn't appear for any other objects. So again, maybe the integrated emission is something that could be even easier to measure. And so this is one of the main hope for.
It's gamma rays, or what is it?
Well, it's, we have calculated both for the low energy channel and for the high energy channel. So if we stay in, take the case in which the lifetime is m squared. This means that in the low energy channel, the integrated emission is for an emission in the radio. And for the high energy channel, it's an integrated emission in the gamma. So the high energy channel is given by the energy of the particles that formed the black hole. So so it means, so it depends. Actually, it's a very interesting.
It's coming from the matter, not. Yeah. It's coming from
photons, basically. Yeah. So there is a very interesting. There is a dependence of this. Of course, this is not just. So this the exact number, the exact energy depends on. Whether the lifetime is m cube or m square, because this means that this means that the black holes have to be formed before or after in the early universe. So there is a precise relation between the mass of the primordial black holes and the temperature at which it was possible to form it. So, but still, everything is around the TIV, and this kind of emission will appear as very high gamma rays. So, in order to fix the idea, low energy channel, it's in the radio waves, high energy channel is in the gamma. Okay. Oh, I missed this. Okay, so now the question is, have we already detected them? So have our friends in the observatories already seen any signal that is compatible with these characteristics? Well, let me start from the high energy component. For this, the thing is that, so there are some gamma ray bursts that, so we have measured signals on the TIV scale, but we know where are they from. On the other hand, we have not measured yet gamma ray burst on the TIV because the telescopes are not big enough. It's really a matter of dimension here. So what you need, so you know, of course, if we wanted to measure those bursts at Earth, we needed to capture the shower of particles created by the burst, and the higher the burst, the larger is the surface on which this shower is distributed. So we have to wait for CTA, for the very large Cherenkov telescope array, in order to have data that could be interesting for our model. On the other hand, there is a new kid on the block. There is a new kind of signal that have puzzled astrophysicists in the last few years, and those are the fast radio bursts. And those bursts don't have yet an explanation. People are rushing to propose models, and of course here we are. We hope that maybe our model could fit this. So the question is, do those bursts have the characteristics that match our model? Yeah, let me compare the two cases. So, yep, here we are. So what they have observed is that there are those bursts that they are in the radio waves, and the measured wavelength is of 20 centimeters. So in our case, the the prediction that we have done so far is for a wavelength that is about half of a millimeter. So this means that there are a couple of order of magnitudes that we have to match. And I hope that more observation of gamma ray burst and a refinement of our model, for instance, including rotation, can make those two numbers closer. Then, of course, the fast radio bursts are very short. They last a few milliseconds, and our process, if you see it from, our process is an explosion, an explosive process, and is by definition very, very fast. They were not able, astrophysicists have tried to point their telescope in the direction from which they were expecting the burst to come, and they were not able to detect any afterglow, nor any other, no repetition, no objects there. So this is very appealing to us. So I put there the possibility in the future maybe to associate to those bursts a gamma ray burst, or maybe even a gravitational wave. Of course, this is a dream. I hope to see it in my life. They are punctual. There is no repetition. I already said so. The energy, the total flux of energy is very large, is enormous. This is what is puzzling astrophysicists, and this is compatible because it's smaller than the total energy that we have predicted. So it could be likely that part of the energy goes into the burst. And well, this is an interesting point that. The estimation is that those bursts may be a very common event in our universe. And so if you believe that those objects may be primordial black holes, we also assume that they should be very common objects all around us. And this gives also hope for future detection. Okay. I think this is everything I wanted to say. I want just to leave you with this last question. So the question is open. Are fast radio bursts bouncing black holes? Well, we cross our fingers. And I would like to hear your questions and your suggestion to improve our model. Thank you very much.
Questions?
Oh.
So you mentioned here at the end the possibility of maybe seeing these models through gravitational waves. How do you see this? How do you model this?
Well, it depends, of course, if the explosion is totally symmetric. I don't think there will be a signal. We need the explosion to be asymmetric. So, but in principle, I expected to have gravitational waves associated with the explosion, and imagining that in the future we will be able to capture very well gravitational waves. So the one possibility is to see for coincidence between one of the signal, whether in the low energy channel or in the high energy channel with the gravitational wave. I don't have more insights about this because I think this is so I'm still waiting for gravitational waves to be detected. So.
I have a naive question about the space-time diagram that you're drawing and the what's going on at the point capital delta. So it naively to me looks like that point is something like a time-like version of a conical excess singularity.
Yeah. I don't know if I don't think there is any conical singularity there.
So how do you resolve that? Because it seems like you started with space-time before you peeled apart the old black hole space-time. You started with a space-time that had too much angle going around in a time-like direction.
Well, my picture of it is that everything is moved there. So in fact, so there was the other picture in which the contracting one and the expanding one are joined together. And then, and then the idea is that you can smoothly connect this two region with a quantum region. And, well,
and it's smooth even when you consider just the physics right around that point.
The point delta,
the
yeah.
classical tip point.
Yeah.
Sorry, the tip was labeled as region 2 in one of the diagrams.
Why do you think it should not be smooth?
I'm just worried that it may look like the time-like version of a conical excess, because the space-time that you started with before you pushed the two regions up and down, you've covered more than once.
Oh yeah, because you mean because of the double covering that we had in the Kruskal?
Yes.
This is a conical singularity.
Yeah,
You
that's
can
the sort
easily smooth it out.
That's and so you're saying that you have smoothed out that tip by adding the quantum space in between. Okay. Okay.
This is a positive conical singularity.
Yeah, I want the other way around. Exactly.
But it's the same.
That was my concern.
Yeah.
Okay.
I don't feel offended if you have also questions to Carlo, and we can both answer. So please, Klaus.
For the formation of the primordial black holes, you have the usual scenarios.
Yeah.
So you don't differ from there. So
No, in fact,
for example, you start from an inflationary phase, and you have the power spectrum, and depending on
yeah.
the details, the formation rate, this is what you use.
Yes.
But there it seems that there were little primordial black holes being produced.
Well, so there, as you
we have this spectral index smaller than 1.9 something from the Planck data.
You mean the spectral? You mean the density contrast, or?
Well, I mean, if you create primordial black holes from the fluctuations that you create in inflation, then it depends on the power spectrum. So it depends on the spectral index. So P of k is proportional to k to the ns,
yes.
the scalar index.
Well,
and the smaller the ns is, the more unlikely it is that you have primordial black hole. So my question is, I think this is a nice scenario, but you need the primordial black holes.
Sure. Well, I am pretty new to the subject because I have started to get interested in primordial black holes very recently because of this work, and so I had the chance to chat, for instance, with Ilya Musko and John Miller, who have done very recently some studies. And in their scenario, the formation of primordial black holes is very likely. In their case, is just because of density fluctuations. So, and what they found is that the density contrast is enough to be 0.45 in order to have the formation of primordial black holes with a very wide spectrum of masses. So, and the measured one is 0.5. So this is below, and so this allows a rich phenomenology of primordial black holes. This is the picture in which I used to think about the formation of primordial black holes. In the last work that we have done with Aurélien Barraud, Weimer, and Bollier, it's true that we have considered also different possibilities. So we mentioned the fact that there could be different possibilities for primordial black holes. For instance, in the case of exotic objects like cosmic strings and so on, then you can have also the formation of primordial black holes, and this has not been taken into account in the study that we have done so far. And well, okay, maybe it's something that we can do in the next work, or maybe I can suggest it to people who likes cosmic strings. So, yeah, Carlo, please, if you have more comments.
One of the reasons people have been interested in primordial black holes is as component of dark matter, of course. So that at some point there was a hope. I believe somebody still have the hope that at least a reasonable component of dark matter could be black holes.
Yeah, this is true. I mean, we have long ago also produced, dark matter by primordial black holes, but there we had to use particular models, not a simple scale-free models of inflation. For example, if you use that Starobinsky model of '92, where you have the inflationary potential, a discontinuity, then you can create many primordial black holes.
Yeah.
So
and
there
you
are
can
models,
fit
there are models.
you can have it the production peak on the
right.
mass that you prefer also.
Right, this you can, but if I go to the very simplest inflationary models, then somehow it seems, at least to what I know, that there are not enough primordial black holes.
If I
Right.
can.
Can I finish? Right, so the question raises how many there are. And there are these results which are not enough, but they're not enough for dark matter. For being detected, if they explode, they could be detected even if they're much less than the ones needed to account for dark matter, or for a part of dark matter.
I think that something that is very exciting to me in this model is the fact that the physics of primordial black hole changes completely, because all the studies that have been done so far, for instance, even the recent papers by Bernard Carr, they all constrain primordial black hole using Hawking radiation. So in this case, Hawking radiation is negligible, and therefore the signal associated with them changes completely, and new phenomenology, maybe also new physics for cosmology and for the physics of structure formation can appear. So, well, I think it's open. And if I can also add one more comment about this, I was mentioning this during my talk, that the best studies that we have so far, excluding primordial black holes as candidate for dark matter, they are coming from microlensing, from, for instance, the Kepler mission. And it's very interesting the fact that they seems not, they don't observe black holes, objects provoking the microlensing that are in the range of between 10 to the 21 and 10 to the 23 kilograms. But as I said, if you believe to this model, all the black holes up to 10 to the 23 kilograms, they have already exploded. So of course you don't see them. There was a question there. I think, no, there.
I think you said that the observed radio bursts tend to have circular polarization.
Oh, yeah.
Does your model say anything about polarization?
Not yet.
Because
No.
obviously it seems like from there's an obvious astrophysical explanation, which would be synchrotron radiation.
Yeah.
So in some sense you're competing
Maybe
with
they're
that.
rotating black holes.
Yeah, or could there be some kind of angular momentum involved that would give a sense of rotation?
Well, we know that most of black holes are rotating at their maximal possible speed, so it's very likely that we have to take this into account in our model. And well, thank you for your suggestion. Actually, this is something we have to do. Yeah.
Yeah, I have a question. What can your model say about the lifetime of the white hole after the black hole is bounced? Like,
Oh, you mean?
yeah. So
No, but well, the idea. So black. Was a confusion that was appearing also before. So the white hole and the black hole are the same thing in this model.
Oh, I see. I see. So you're referring to the bounce process, the white hole in the classical sense.
So there is a point.
Reverse of
So the point is to see.
Symmetric.
Yeah.
Right.
So the lifetime that we are computing is the time between when the horizon of the black hole forms and when the trapping surface of the white hole disappears, let's say.
I
So
see.
this is, and but maybe I wanted to add something because this was not coming out from the previous talk of Carlo. So there is this picture of the tunneling, and it's very. For me, the inspiration for this work came from loop quantum cosmology, in which what you have is that, so you model the time with some scalar field, and this is in the case of cosmology. So here you have the scale factor, and so you have a contracting, so this is an expanding solution, and you have an expanding, a contracting solution for the universe. And what you see using the effective equation of loop quantum gravity is that, so the points of the numerical, associated with the quantum equation goes this way. So there is a point in which the quantum trajectory goes from one curve to the other, and you can see it also in the numerical simulations. So this is what we call a tunneling, also in this case. There is a moment in which all the matter stops to collapse because of the quantum effects, instead you have repulsion and you have an explosion. Yeah.
The wave function of the universe, you have two branches, and you cannot say that you are on one branch and that you follow a trajectory to another one. In quantum mechanics, when you have a stationary wave, it's a superposition of incoming and outgoing wave, and you cannot say that you are first on the incoming part and then you bounce and go on the outgoing part.
Well,
I don't understand what you say.
So the idea is that you take a semi-classical wave packet, and you follow these semi-classical wave packets back in time, and it gets close to the Big Bang, but at a certain point, you see...
Classical approximation is not anymore valid, that you insist on this point.
So, yeah, well...
But that's the point. But so you use the full quantum equations, you evolve the wave packet, and you see what happens. And what happens is that instead of following the classical trajectory, which would be to go smaller and smaller, it continues on the other.
But how could you put a narrower time in this description? There's just two parameters, a scalar field and a geometrical factor. There's no time.
Oh, the general relativity.
Well, the scalar field is introduced as a clock in order to...
It's an intrinsic time. Look, there's a half a century discussion on that. So
no, I understand.
The T parameter, it's gauge in GR, so you just express the evolution in terms of relative evolution of one variable with respect to another one. And you can arbitrarily choose.
I agree that there is a long discussion about it, but I disagree with the interpretation of the proposal of solution you advanced. Okay.
I agree that this region is a region in which you are in the full quantum regime, and instead of using semi-classical equations, you want to use the full quantum gravity theory. But in fact, you can do this and make this picture credible on the basis of the result in the full theory. So maybe we can discuss. I would be happy to discuss this more with you because I think it's related with some of your work. So.
So do your calculations in loop quantum gravity give you any concrete information about the quantum region of space-time that's involved?
Good question. No. So, no. Like the functional integral doesn't, in a sense. The transition amplitude it's computed order by order in some approximation. So it's a truncation. So to a given order, we just have a number associated to initial state and a final state. Of course, initial state you can, given a classical metric, you need the classical metric and the extrinsic curvature, right? You need P and Q, initial and P and Q final. And then you want to see what is the probability amplitude of going from one to the other. And that's like an overlap of wave packets. So it would be like you have all the wave packets very close to the wall and then see what's the probability of being the other side of the wall, in a sense. So you don't have an information from this kind of calculation about the trajectory of the particle through the wall.
But you could have some kind of expectation of, the most likely position as it evolves.
Yes.
I mean, this is the kind of thing that Klaus and Peter were able to do.
Yes. So far, I would say no, because at least in the first order truncations we're using, there's very little we can say about the intermediate states. Maybe to higher order, less truncations, higher order approximation, we could say more, but on the other hand, the hope is that those are not needed, because otherwise we can't do the calculations.
Well, if I can just say one thing, just to be sure, we don't know exactly, but for sure it's not singular. So there is no singularity there because of... Well,
Yeah, I wasn't worried about that. I was
Okay.
worried about causal behavior where, say, Aricle's constant lines are effectively space-like or time-like.
Yeah.
Because they have to change in that region. I wondered if you could explore that.
Yeah, there is a, it's like, so inside Aricle constant is obviously space-like.
Not everywhere.
Sorry?
Not everywhere.
Inside, yeah, but outside, very much inside there, so very much outside not, right,
Right.
exactly. Yeah, I don't know, no idea.
So in particular, what affects what you would portray as the apparent horizon in this discussion?
In a sense, the interesting thing is not what happened. At this point, the interesting thing is not what happened at R equals 0. It's what happened near the tip of the thing.
Right,
So,
yes, I agree, totally.
Yeah.
Yeah.
I agree.
Yeah, so just to elaborate about R equals 0, in what you plot, it looks as though the shell is going to R equals 0, but in fact it's only getting to this R min that you've calculated, so it's spatially separated from 0.
Yeah, R equals 0 doesn't exist. Yeah,
Right.
that's right.
Well, it exists as something regular.
Yeah.
So that raised another question. That means that around the edge of the shell, you have a flat region that's everywhere flat. And so you must be able to actually join those flat regions together in some smooth way.
You mean inside?
So inside the shell, yes.
Yeah.
So inside R min, which is very small, 10 to the minus 12 centimeters or something, but logarithmically it's far away from 0.
Yeah. The gray region is flat, so we should, the past gray region and the future gray region, in a sense, can be joined.
Right.
Yeah.
So they can be. Have you actually done that? Or
The actual quantum region is only this funny shape one there. So if I follow around r equals 0, let me put it this way: nothing prevents me to write the bounds just a little bit, just a finite r, and inside have a continuity between the past flat region and the future quantum region. What I'm saying that if I'm inside the shell, I expect that basically I don't see anything. I see the shell approaching and then bouncing out. And if I am very, very small in r equals 0, I just have my clock.
well, the question is when you try and match those two flat regions, whether you basically have to be strongly redshifted or blue shifted from the shell in order to get the matching to be smooth. I mean, it's not totally trivial.
No, we wrote, in fact, in the paper, we wrote metric for the quantum region, an effective metric, which we don't want to give particular importance to, but nevertheless, we wrote it exactly to answer these questions, like the question that she raised about smoothness. So we, in fact, have a metric filling up everything, which is just written somehow smoothly joining. And in that metric, which fails to satisfy the Einstein, in fact, fails to have satisfy the energy conditions in the quantum region, basically it goes smoothly to flatness when you go to r equals 0, and the dramatic things happen in the region where you were mentioning is outside, because the dramatic thing, in the sense you have to, the light cones bent in before t equals 0, and then quite rapidly they have to bend out.
So I think there is something dramatic happening at the bounce, because this is one point where I'd like to disagree with Francesca's diagram. I would argue that the apparent horizon, or the trapped region, is bounded by the collapsing shell and the expanding shell, and there's only one trapped region, not two. And on the outward going, they're bounded by the two parts that were the horizon.
No, you need two. You need two. If you fill out the metric, you need two by continuity, by a topology. There's a topological thing that prevents it to be one. A trapped region is where r equal constant becomes inside it's space-like and outside is time-like. Okay?
Yes.
But r equal constant can be space-like in two different manners. By r equal constant is like that on Minkowski, but it can be space-like this way or space-like the other way. And you cannot go continuously from one to the other. To going space-like this way, this is spherical symmetric. So
Okay.
to space-like the other way, you have to go through time-like. So therefore, the trapped region upstairs and the trapped region downstairs must be separated by a region which is not trapped, which is where the r equal constant from time-like goes back to, from space-like goes back to time-like and space-like again. We got long confusion about that, because that's what was preventing us to write this metric at first time, because we were, initially everybody had been thinking about a single trapped region. The single trapped region is not compatible with a white hole and a black hole for the reason I just said.
But it must be bound by the shell, because the shell takes you, once the shell goes inside the horizon, it's bound by time-like.
Yeah, it's bound by the shell, I agree. Bound by the shell.
So then it must go to the point where the shells intersect. The apparent horizon must, each portion must go to the point where the shells intersect.
No, the
Yes.
inner horizon can separate from the shell earlier if you allow the Einstein equation to be violated.
Well, if it's exactly Schwarzschild outside, that wouldn't happen. So
If it is
it
exactly?
So what you originally were doing was mapping flat space and Schwarzschild, and the only part that you were changing was this little quantum wedge.
Yes. So inside the quantum wedge, at some point, the trapped region has to separate. So we're still in the quantum region, but in my effective metric, the inner horizon separates from the shell and comes in. The light cone on t equals 0 must be symmetric. They can be neither this way nor that way.
No.
So r equals 0 must be perfectly vertical in that diagram by symmetry. So,
Well,
we are violating the Einstein equations inside
Yes.
the
okay.
so
So I think if you do the matching, it's not necessarily, it doesn't have to be true that r equals 0 is vertical. It only has to happen that it's not space-like. It could still be symmetric even if it's not vertical. So it could.
no, it's not symmetric.
would-
To be
it would-
symmetric in
it would
t
go like
in
this,
t equal
yes.
minus, yeah. If you do that, at t equals 0, you must be.
Right. Yes.
This has been all the endless confusion we went through when we wrote this metric with Hal. Yeah.
Oh,
Yes. Yes. Go on.
I have a question for this outstanding audience, because probably the most interesting thing to do after finding this metric is not to go directly to rotating black holes, but maybe to try to find a solution for not a shell, but a dense sphere. So I was wondering if any of you have has an idea about how this metric for a dense collapsing sphere should look like, and if you have suggestions.
Your shell is freely falling, there's no equation of state or anything, it's just freely falling.
Well, you can use the equation of state for photons, because basically what is forming is just radiation, yeah. Yeah, okay. So you think it's not more challenging than what has been already done? Oh, yeah. Mhm. Yeah.
Anyway, if these are formed in the early universe, they're mostly neutrinos and photons and so forth. There's very little, not much matter.
Yeah.
So I don't know what comes out.
Photons and neutrinos. Photons, that's what I expect to come out.
Well, even though the explosion then gives some production of quarks, and then.
Fast radicals of photons, gamma rays of photons.
Well, the high energy signal during the explosion can make the appearance of of gluons. And then what you see is, so in fact, I forgot to mention this during my talk, that in the last paper, what we have done was, for the high energy signal, was to use a code that is called PIZIA. It's a standard tool for high energy process, and so we have studied all the production of these particles.
Okay, well, I think we've reached the limit of our time. The crowd is dwindling, the staff are exhausted, and we should thank our speakers again.
Thank you.